Hi, dears. In the last session, we discussed until the image formation by a concave mirror when the object is placed between the center of curvature and focus. Okay, so we'll be continuing and going further from here. So the ray diagram. And now the image formation by a concave mirror when the object is placed at focus. When the object is placed at focus, the parallel rays that that hit the object and go to the concave mirror will be passing through the focus. Any parallel ray will always be passing through the focus. They're parallel to the principal axis will be passing through the focus. The reflected ray will be passing through the focus. And here you see this. And here also the parallel ray parallel to the principal axis. The incident ray and the reflected rays passing through the focus. The next ray here, we are taking a ray that will be going through the center of curvature, touching the object and then hitting the concave mirror. So the law says the ray which is passing through the center of curvature will trace back the same path. So here, this incident ray and the reflected ray will be tracing back the same path. And here is a demonstration where the second ray is passing through the principal focus. You only have to draw two rays when you draw a ray diagram. So here, this ray is passing through the second ray is passing to the pole. It will make the normal with the principal axis. Will trace back the same I is equal to R with the normal and will be reflected obliquely and following the laws of reflection. See the characteristic of these two reflected rays. Be these two rays or be these two rays, they are parallel. They are parallel rays. So what is, will parallel rays make an image? So we know that parallel rays will never meet. But we in physics, we believe that the parallel rays will meet somewhere in infinity and create an object at infinity. So here we believe that the image is formed at infinity. The image, so see the parallel rays is going in front of the mirror. And so where the image is formed in front of the mirror, it's going to be a real image. So any image which is formed in front of the mirror is going to be a real image. It's an inverted image. And when the object is placed at focus, it's a highly enlarged image. Here, I want to bring an analogy here. When the object was placed at infinity, let me see if I can take that slide. Yeah. When the object was placed at infinity, the image was formed at focus. And at infinity, the image is an enlarged image here. And the object is an enlarged object and you get a point-sized image at focus. Okay. This will be just the opposite when the object is placed at focus. Okay, think it this way. This is a point to recollect, the tips and tricks to recollect. Okay, when the object is placed at focus, see how you should think. The focus, the object is this big, right? So when the object is this big, we are expecting a very large image which is formed at infinity. So the image is formed at infinity. It's in front of the mirror. It's a real, inverted, and highly enlarged image. And now the last ray diagram. So when the image formation by a concave mirror, when the object is placed in between the focus and the pole. So when the object is placed in between the focus and the pole, see the first light ray will be say that it touches the object and it will be going parallel and hitting the incident ray will be hitting the concave mirror. So following the laws of reflection, where it will trace back, it will go through the focus. The second ray we are tracing here, we are tracing a line, a ray that will go to the pole. Following the laws of reflection, I is equal to R, it will be getting reflected obliquely. The characteristics, if these two reflected rays they are diverging rays. They are going in two different directions, right? So when the rays are kind of diverging rays, they will never meet. Okay. Here you have the first ray shown as hitting the pole, then makes the I is equal to R and is getting reflected obliquely like this. So in this picture, it's more evident. The ray that passes through the center of curvature will touch the image, and the incident ray will hit the concave mirror, and this reflected ray will be tracing back the same path. So it will trace back the same path here. So these two rays are the two rays are diverging rays. But if you look at a concave mirror, you get an image, right? So how is it image? You get an image which is appearing to come from behind the mirror, behind the concave mirror. So where is the image formed? The image is formed far behind the mirror. Image is a virtual and erect and enlarged image. Whenever the image is formed behind the mirror, it is going to be erect and virtual. Okay, so in this case, because the object is placed in between focus and the pole, the image that is formed will be an enlarged image, and also it is formed behind the mirror. It is erect and it is enlarged. So whenever the image is formed behind the mirror, it's virtual and erect. You already know that. The next thing that you'll have to know is because it is placed in between F and P, it's going to be an enlarged image. Now, the image formation by this is a summary of what this is the NCERT summary that is there in your textbook. If you will have to clearly draw the ray diagrams and study the ray diagrams. Once you do that, this is just a summary of the theory part. Yeah, and now the use of concave mirrors. This comes as many PYQs. Okay, so the concave mirrors are used extensively in many areas. Okay, one use is that it is used in torches or searchlights or vehicle headlights and all. Why we use why we use the concave mirror in torches or the searchlights or vehicle headlights? We want a parallel stream of light in that case. So we use a concave mirror. So when does a concave mirror give us a parallel stream of light? When the bulb is placed at F. Let me show you that. Yeah. See, if the bulb is placed, so this is a concave mirror of a headlight, you imagine, okay? And here the bulb is kept. So how is the ray going to come? From the bulb, the light ray will go and hit the concave mirror, and the rays are going to be parallel stream of light. And that's what you want to know. You want in case of a torch light or a headlight of a vehicle, or a searchlight, all those, you want a parallel stream of light. So you use a concave mirror, but the concave mirror will give the image or the parallel stream of light when the bulb or the object is placed at the point F. Then it is also used as shaving mirrors or the mouth mirrors, which are used by dentists. The dentist will use a mouth mirror. It's called, and it will enlarge. It will show a big image of the tooth for the doctor to work with. Or the shaving mirrors, they show an enlarged image of that part of the face. So, in order for you to have an enlarged image, where do you want the object to be placed? The object has to be placed past C. As I have told you before, whenever the object is placed at infinity or anyway beyond C, it is going to be a small image. See, whenever it is passed beyond C, it's going to be a small image. But and at C, you get a same image of the same size. But if you are putting the object in between past C and in between C and P, you're going to get an enlarged image. So you have your image, your object should be somewhere past C towards P, towards the center. It should be past the center of curvature towards the pole. Okay. Then, yeah. It is also used as solar concentrators to produce the heat in solar furnaces. you would have done that experiment where you focus a light beam with a concave mirror and you get a spot image, which is actually the image of the sun. You keep some papers there, you get to see that the paper sometimes, or the if it's tissue and all, it will easily catch fire. How does it catch fire? Because the light rays are getting concentrated at that particular point, or where the image of the sun is formed. So you concentrate, the sun is at infinity. So you concentrate those parallel beams, and the concave mirror will converge it into a focus where you get a point size image of the sun. So what is the law of thermodynamics states? Energy can neither be converted, can only be converted from one form to the other. So here the light ray, it is all getting converged to that particular point, and there it produces what? It's going to produce a heat energy due to the convergence of the light ray at that particular point F. So in the solar furnaces, what you have is the concave mirror will focus the sunlight, and the light ray will get focused to that particular point at F, where the coil is there. So the coil will get heated up, and using that heat, we will the furnaces is used to power I mean, that gets heated up, and that will get that there you use it for the coil will get heated up, and the coil that heat is used to cook your food. So that's how you concentrate the sunlight in solar concentrators. So in that case, where is the image? Where the image is formed at F, and because the sun is at infinity. Okay. And use the concave mirrors are quite important. And now the image formation by a convex mirror. So in convex mirror, you have only two positions, right? Why? Because the center of focus and center of curvature is behind the mirror, so they are imaginary points. You cannot get it. So only point that is there in front is the pole, right? And when the object is at infinity, what happens? The light ray will hit the concave mirror, and it will get diverged in tracing the eye, following the law of reflection as I is equal to R. But if you extend this reflected ray, it will appear to get diverged from the point F, and here is the focus. So whenever the object is placed at infinity, the image is formed at focus, because these reflected light rays will appear to come from the point for F. Okay, and so the image is formed at F at the focus when the object is placed at infinity. The image is formed behind the mirror. Any image that is formed behind the mirror is going to be a virtual and erect image. And whenever the object is at infinity, the image is going to be at focus, and it is going to be a diminished or a very small or a point-sized image. Okay, so this is how this is the characteristics of the image formed by a convex mirror when the object is at infinity. And now the image formation by a convex mirror when the object is placed at a finite distance from the mirror. So what is the pole? Pole is the geometric center of the convex mirror. Okay, here is a pole. Yeah, here is a pole. You have M and N as the aperture of the convex mirror. The object is placed at a finite distance, that is AB is the object, and from the mirror. So the parallel ray, which is parallel to the incident ray, which is parallel to the principal axis, will go and hit the convex mirror, tracing the I is equal to R. It will get reflected towards this side. Well, because here is a normal, because why you put the normal here, the curvature is towards this side. Okay, so and the next ray, which is aimed at the center of curvature, it will trace back the same path. So I and R will be in the same direction. Will be the same ray. Okay, the R will be tracing back the same path as the incident ray. So you put both the arrows here, and where is and these two lines, if you extend these reflected rays, these two lines will appear to join here to meet at this particular point, and this is where the image is formed. So what is the characteristics of this image when compared to the object? It is going to be a very small image. Okay, so image is formed between the pole and the focus of the convex mirror, The image is formed behind the mirror. Any image formed behind the mirror is going to be virtual and erect. And the image is a small image. These are the characteristics of the image by a convex mirror when the object is at a finite distance between from the mirror. Okay, image is formed between the pole and the focus is behind the mirror, virtual, erect, and the image is diminished or small. And this is exactly the table given by the NCRT, the summarization of what we have just discussed. And remember, convex mirror will only give you virtual images. Okay, they will never give you convex mirror. Okay, convex mirror can only give you virtual image, while concave mirror will give you virtual as well as real images based on where the object is placed. Okay, concave mirror will give a virtual image only when the point object is placed between F and P. Okay, remember that it comes in as PYQ in many question papers. So the concave mirror will give you a virtual image only and only when the point object is placed between F and P. You want to see um, the previous session. So this is the only virtual image which is formed by the concave mirror. Okay. No, all the other images are real images. While only when the object is placed between F and P, concave mirror will give you a virtual image. And while in the case of a convex mirror, it will only give you virtual images. And use of convex mirrors, it is used as rear view mirrors in the vehicles and safety mirrors. Rear view mirrors, if you see the vehicle rear view mirrors, very long before in 1980s like that, it used to be plain mirrors only. But later on, all the vehicles started having convex mirrors. Why you use a convex mirror? Because you get a wider field of view. You get more field gets enclosed in. Your mirror will be able to capture more view of the road, so you use it as a rear view mirror. And but if you notice the rear view mirrors, there's a sticker that will be placed on the rear view mirror saying the object will be far more closer to you. I don't clearly remember that. I believe it's like the object appears to be smaller than or closer to you than I don't remember that so well, but there is a statement that is declared on the convex mirror. The object appears to be more closer to you than that is shown in the mirror. Okay, why? Because the convex mirror will give you a small sized image. So the car or a vehicle which is behind you will appear quite smaller in your rear view mirror, but it will give a bigger view. The view of the convex mirror will be more, so you will get a more field in your rear view mirror. Okay, safety mirrors are nothing that they are those mirrors that are kept on different hairpin turns, or when you go uphill, you can see these safety mirrors, or sometimes at the T junctions where you don't have where the driver will not have a greater view of the road. They place safety mirrors such that the driver coming from the opposite side can have a clear view of the road. Okay. Mm. And now the sign convention for the reflection by spherical mirrors, the new Cartesian sign convention. I'll show you the picture first. This is easier. This sign conversion or the new Cartesian sign convention will be applied for solving all the problems in this spherical mirrors. So see, this is the Cartesian sign convention. Okay, this picture explains this. So if you draw your x-axis and y-axis in your maths, so how do? You do an x prime, and you also have see at the point. This is the spherical mirror, so it's a concave mirror. As you see, it's a reflecting surface, and this is a hard surface. So you're putting a tangent which will touch this mirror at P. So how will this be? This will be the y-axis, and this will be the positive y, and towards downside will be the y prime, or the negative side. So this is exactly the sign, what the Cartesian sign convention says. That is, this P will be taken, that is, as the origin. That is, in the x and y axis. Here, this is the P will be the origin. O will be the origin, right? So in this convention, this instead of O, this P will be the pole is considered as the origin of the origin. Um, the um, the object is always expected to be at the left hand side of the mirror, of the reflecting surface. So if the object is here, which means the light will be hitting the concave mirror, the incident ray will be coming from the left hand side of the mirror. Okay, then all the images that are formed towards this side, that is this quadrant, will be positive. Towards this positive x-axis will be positive. All the distances that are taken above, all the images that are formed above that is towards the positive y, will be taken as positive, and below that is towards the negative y, will be taken as negative, and towards the left hand side will be taken as that is towards this quadrant, that is towards the left hand side of the x-axis, will be taken as negative. This is what the Cartesian sign convention says. And this is quite important as we deal with the problems. So P is the origin. The principal axis of the mirror is taken as the x prime, and all the object is always placed at the left hand side of the mirror, which means the left LHS will in your left hand side only, there only the incident light will come. So all distances that are parallel to the principal axis will be measured from the pole. That is, say for example, this is your AB, that is the object, and you wanted to know the object distance. So what is the object distance? It will be measured from the pole to B. Okay, so the object is here. So that distance that you will be taken from the pole, that is any measurement which you are taking parallel to the principal axis, will be taken from the pole. And all distances that are measured to the right of the origin are taken as positive, and the left hand side is taken as negative. All distances, that is the same thing that I said before, that all towards this RHS will be the RHS side will be positive. The measurements that are taken upwards will also be positive. The measurements that are taken downwards will be negative, and towards the left hand side will also be negative. Okay, so apply this in all the problems. So yeah, the mirror formula of the spherical mirrors: 1 by v plus 1 by u is 1 by f. That is, u is the image object distance, v is the image distance, that is object distance from the pole. Image distance also will be measured from the pole, and one that is equal to 1 by v plus 1 by u will be the 1 by for f, that is the focal length will be 1 by f. The reciprocal value of the focal length will be 1 by v plus 1 by u. This formula will be valid for all the spherical mirrors in all the situations and for all the positions of the object. So whenever you see it's a spherical mirror, you can, and you wanted to find the focal length, this is the formula that you have to use. And now the magnification. Magnification means it is like how big or how like what is the magnification of this particular lens or a particular mirror, which means what? How much times the object is magnified, or how big has that has become from the or how much times it has become the image has is being magnified. Okay, so it gives the relative extent to which the image of an object is magnified with respect to the object size. That is, if you have the image as say 100, and the object of the height of the object is say like 10, so the magnification will be 10. 10 into 10 is 100, right? So magnification of that particular mirror will be the height of the image divided by the height of the object. That is, the height of the image is 10 times it has become bigger than the object. That's why we say it is the relative extent to which the image of an object is magnified. It has the object size has become 10 times more than that of the image size has become 10 times more than that of the object size. So in that case, we'll say, okay, 10 is the magnification. Okay, that is, I just said as an example, if the image height is 100 and the object height is 10, which means the magnification will be 10. That is, object has become 10 times more bigger, magnified in size than the image has become 10 times more magnified in size than the object. And okay, M and H, that is magnification, and the height will always be positive for virtual images and negative for real images. You can see that virtual images will be formed there. The virtual images will always be formed towards the um towards the right hand side of this principal axis. So in this case, all the virtual images will be falling on this part, right? While the real images will be coming in towards as inverted images. They will be inverted images, and they'll be they'll be real images will be coming to the left hand side quadrant. So this quadrant will be positive. So all the real images, all the virtual images will be positive. So M and H will be positive for virtual images, while and M and H, that is the magnification, and H will be a height of the image will be negative for real images, because the real images will be forming in this particular quadrant. And also we'll have to remember that the magnitude, if the modulus of the magnification is equal to 1, the object size and the image size is equal. Okay. If that modulus means minus 10, you will take only the magnitude. We will not be taking the sign of it. If you say the image is minus 10, we will not, the magnification is minus 10. We will modulus of that minus 10 will be 10. That is, we will be only taking the magnitude. We will not be looking into the direction, or we will not be looking into the vector quantity there. So the modulus of magnitude is greater than 1 means it is the image is a large image, while the modulus of the magnitude is less than 1 means it's a small image. The image formed is smaller than the object size. While the magnification is greater than 1, the image size is greater than or the larger than the object size. Okay. Yeah, these are the equations that are there in the reflection of equations for the reflection of light by the spherical mirrors. The first one, as we discussed, the focal length is half the radius of curvature, or we can otherwise say that radius of curvature is twice the focal length. And the mirror formula, 1 by V plus 1 by U is equal to 1 by F. This can be simplified if you cross multiply. You will get this value as F is equal to UV plus U plus V. As I'll be using the whiteboard very soon, so I'll be able to do the problems for you. And the magnification, M is equal to the height of the image, H prime, by the height of the object, which we can otherwise say it as minus V by U. That is, the height of the image is nothing but the object's distance, right? So minus V by U, that is this minus sign we should never forget. The minus V will be the image distance divided by the object distance. We'll be discussing the questions in the next session. And thank you for your attention, and make the concepts clear as we will be discussing the problems in the next session. Thank you.